yesterday we looked through the history of medicine and we got to the start of the modern era, and I pegged that against this drug Salvarsan in particular, which was used to treat syphilis. And the reason that leads us nicely into today's lecture is that today and tomorrow we're going to be talking about bacterial infections and ways in which chemistry during the 20th century approached the treatment of bacterial infections. It's kind of worth reflecting, if you look at life expectancy through history, that it has this kind of relationship. For very many years, life expectancy was around 35 years. That doesn't mean the longest anyone lived was 35 years. It means the average that anyone lived was 35 years. Many people died as children, many people died young, many people died in childbirth, and that kept the average very low. And it was only really during the industrialized Victorian era, 1900, that in the West these figures began to change, and now the rest of the world the figures are changing as well. And so the life expectancies that we all expect nowadays of 80 years are purely really a construct of the last 100 years. They're underpinned by science. It's a whole set of things that underpin this data. It's better surgical practices, it's better healthcare practices, it's better health and safety in the workplace. We don't send children up chimneys anymore so they don't get cancer when they're teenagers, and all these kinds of things. But fundamentally, amongst the medicinal chemistry things that have had the most impact on life expectancy figures, antibiotic drugs are the number one. And we're going to tell the story of antibacterial drugs in today and tomorrow's lectures. So bacterial infections are ubiquitous. They're cellular life forms. They live irrespective of us. We are, of course, colonized with bacteria. We have many bacteria that do us no harm whatsoever, particularly the gut flora. You can argue that a human being is actually, apart from our own cells, a collection of bacteria. Without bacteria, we don't function. But there are some of these bacteria that cause problems, and they're the ones that are on the slide there. These are ones that either use essential nutrients that our cells need, or they produce byproducts that are toxic to us. Those are the reasons that bacteria are bad for us. It's not the bacteria per se, it's that they're using the things we need or producing things that damage us, and those are the ones that we then consider to be infectious and bad bacteria. And of course they can transmit from people to people because they can survive outside of the human body, and so there's a way that they can transmit quite easily. There are many of them there. In terms of the number of bacteria, the most significant are the Streptococcus and the Staphylococcus. And this is one of the reasons that people are so worried about MRSA, methicillin-resistant Staphylococcus aureus, that we'll talk about as we go through this lecture course. So this is bacteria, and amongst these there is a bacterium actually associated with syphilis. And that's the one that we're specifically considering when we want to understand Paul Ehrlich's breakthrough in more detail. So at the bottom of page 11, as it says, the story of antibiotics started with Salvarsan. Now, Salvarsan is not an antibiotic in its own right, but it was the start of the story. Just let me put a bit more desk light on. Started with Salvarsan, and it was not long until chemical companies started seeking alternative antibacterial agents with a much broader spectrum of activity, because Salvarsan only really works against the syphilis bacterium. And before we move on and think about other antibiotics, we're going to think a little bit more about how and why Salvarsan works. So the first thing to note here is that Salvarsan works by releasing an active agent in vivo. It is converted to the active form by the body. So it's not the actual drug structure that I showed you that is the active agent. The body turns it into something that is active. We refer to this as a prodrug. Salvarsan, the structure that you saw, is a prodrug. It turns into a drug. This is a concept that we'll come back to in general terms in lecture 7. So what happens to it? We refer to this as a prodrug. If you flip over onto page 12, you will see what's happening to Salvarsan in the body. So I'll just zoom in a bit on this. We have the structure here in abbreviated form. This is our prodrug. In the body, we get oxidation in vivo, and it breaks that arsenic-arsenic bond. And you generate this active form of the drug. The reason that works is that sulfur then likes to bond to arsenic. In terms of inorganic chemistry, they're both soft species. Sulfur is soft. In terms of organic chemistry, you can think of the sulfur as a good nucleophile attacking that arsenic-oxygen double bond. Ultimately, you'll lose water and you'll attach two sulfurs to the arsenic. It's a bit like it is a thioacetal that you're making at the arsenic centre. And because this is an enzyme, this is the cysteine amino acid. The enzyme gets attached to arsenic. And what that can do, in many cases, is it deactivates the enzyme. So why is it useful to deactivate enzymes with cysteine in? Why does Salvarsan act as a magic bullet? Well, although Paul Ehrlich didn't know it at the time, it wasn't designed to do this, syphilis bacteria contain far more thiol-containing enzymes than human cells. It's just the way the syphilis bacterium had evolved. It has a lot of cysteines playing very important roles in the bacterium, much more so than our cells. So if you've got a chemical that will deactivate cysteine-containing enzymes, it will relatively specifically damage the syphilis bacterium more than the human host if you get the dose right. Of course, this is why mercury salts had worked a bit against syphilis, because mercury will do exactly the same thing. Mercury will bind to sulfur-containing enzymes. It was just a bit less specific and a bit less controllable than this new arsenic form of the drug that Paul Ehrlich developed. So fundamentally, we'll just write the conclusion. Syphilis is more affected by Salvarsan than you. You're still affected, but not so badly. And given the syphilis is going to kill you, this is a breakthrough, and it's why Salvarsan is called a magic bullet. And eventually, it was prescribed in the active form. So they stopped giving Salvarsan as a prodrug, they just gave this arsenic oxide directly to patients, once they understood what was happening. Nobody uses Salvarsan anymore. It's not a drug you'll get. If you get given syphilis, you get given modern broad-spectrum antibiotics, okay? So it's not a drug in modern use. But it illustrates something really important. The way you target bacteria is you have to find something that's different about the bacteria to the human cells. If you can find something that's different in bacteria and target it, you will kill the bacteria without damaging human cells. And that's a fundamental principle of how you develop any drug to treat an infective agent. You've got to find something specific about that infective agent.